Hello friends. Now in this video we are going to look at comprehensive RF measurement techniques with SDR, setup, tools, and procedures. Let's get started.
Here we have a setup and list of measurements typically performed for characterizing an RF device under test, DUT, like an SDR, software-defined radio. Here's a breakdown of each measurement listed and how to perform them practically using the depicted setup. Measurement setup components. Signal generator provides a controlled input signal to the DUT at varying frequencies and power levels. RF switch routes signals to different measurement devices, signal analyzer, power meter. SDR DUT, device under test, which could be an SDR or other RF device. Signal analyzer measures various parameters like gain, noise figure, and phase noise. Power meter accurately measures the output power from the DUT. Controlling computer automates the process, adjusts settings, and records data. First one, gain power calibration versus frequency. Goal, measure how the gain or output power of the DUT varies with frequency. Procedure, set the signal generator to sweep across the desired frequency range. Measure the output power of the DUT using the power meter or signal analyzer. Calculate gain by comparing input and output power. Repeat for each frequency to plot gain versus frequency. Second one, noise floor and noise figure versus frequency. Goal, determine the lowest signal level the DUT can detect, noise floor, and calculate its noise figure. Procedure, with no input signal, measure the output power of the DUT, which represents the noise floor. Use the signal analyzer's noise figure measurement feature or calculate noise figure using known parameters, e.g., gain, bandwidth. Perform the measurement at various frequencies to plot noise figure versus frequency. Third one, 1 dB compression point versus frequency. Goal, identify the input power level where the gain of the DUT drops by 1 dB, known as the 1 dB compression point. Procedure, increase the input power from the signal generator until you observe a 1 dB reduction in output gain, compared to linear gain. Record the input power at this point and repeat the test at different frequencies to assess how the compression point varies with frequency. Fourth one, self-generated spurious response. Goal, detect any unwanted signals generated by the DUT that are not part of the input signal. Procedure, with a fixed input signal, monitor the output spectrum on the signal analyzer. Identify and measure any spurious signals that do not correspond to the input frequency or harmonics, noting their levels and frequencies. Fifth one, dynamic range versus gain. Goal, measure the range between the noise floor and the 1 dB compression point across different gain settings. Procedure, set the DUT at a specific gain level, measure the noise floor and the 1 dB compression point. Calculate the dynamic range as the difference between these 2 points. Repeat for various gain levels to see how dynamic range changes with gain. Sixth one, IP2 and IP3 vs frequency and gain. Goal, measure second order and third order intercept points, IP2 and IP3, indicators of the DUT's linearity. Procedure, use two-tone signals from the signal generator. Monitor the output on the signal analyzer for intermodulation products. Adjust the input level and calculate IP2 and IP3 based on the power of the fundamental and intermodulation tones. Perform this test at various frequencies and gain settings. Seventh one, phase noise measurement. Goal, assess the short-term frequency stability of the DUT by measuring phase noise. Procedure, set the signal generator to a fixed frequency. Use the signal analyzer to measure phase noise, which appears as sidebands around the main signal. Plot the phase noise at different offset frequencies to assess stability. Last one, long-term stability. Goal, measure the DUT stability over an extended period. Procedure, set the DUT to a fixed frequency and power output. Record the output power periodically over hours or days using the power meter or signal analyzer. Plot the results to observe any drift or fluctuations over time. By following these procedures, you can comprehensively characterize the performance of an RF device across various parameters using the setup. Thank you and meet you in the next video.